December 28th, 1879. The Tay Bridge in Scotland collapses during a storm, taking an entire passenger train with it. 75 people plunge into the black water below. News spreads like wildfire across Britain, and suddenly every Victorian railway engineer wakes up in a cold sweat, mentally running calculations they'd signed off on years earlier. Here's what nobody tells you about that moment. It wasn't just the Tay that had engineers terrified. There were dozens of bridges built in that same era, using similar math, similar materials, similar rushed construction timelines. And one of them, the Eads Bridge in St. Louis, should have been next. Picture this, March 1890. The Mississippi River is in full flood, running higher and faster than anyone's seen in decades. Ice chunks the size of carriages are slamming into the bridge piers. A freight train, overloaded naturally, because this is the Gilded Age and nobody respected weight limits, is crossing at the exact moment a steamboat passes underneath, its tall smokestacks clearing the arches by inches. The bridge is groaning. Workers on the riverbank are literally taking bets on whether it'll hold. Chief Engineer James Eads had been dead for 7 years by then. The man who'd staked his entire reputation on this bridge wasn't around to defend his creation, and the whispers had been growing louder. Eads got lucky. Those arches are too thin. The steel isn't strong enough. It's only a matter of time. What made engineers particularly nervous was the bridge's central span. 520 feet of steel arching over the Mississippi, the longest arch ever attempted at that scale. The calculations required to make that work were so complex that most engineers of the era simply didn't believe them. When Eads first proposed the design in 1867, 14 of the country's most respected engineers publicly declared it would collapse under its own weight. Not might collapse. Would collapse. Yet there it stood, 13 years later, during the worst flood in memory, still carrying trains that were heavier than anything Eads had designed for. The real fear wasn't just structural failure, it was the humiliation. If this bridge came down, it would vindicate every skeptic who'd called the entire steel arch concept a dangerous fantasy. The entire future of American bridge engineering was quite literally hanging in the balance, waiting for the Mississippi to make its verdict. The flood peaked, the bridge held, and nobody could quite explain why. Let's talk about how this supposedly doomed structure actually got built, because the story is messier than any engineering textbook will admit. James Buchanan Eads was not, technically speaking, a bridge engineer. He was a salvage diver. The man had spent 20 years walking along the bottom of the Mississippi River in a diving bell, pulling up sunken steamboats. He knew the river intimately, its currents, its moods, its geology, but he'd never designed a bridge in his life. When St. Louis needed to span the Mississippi in 1867, they hired him anyway, because he had one thing the professional engineers didn't: absolute confidence that it could be done. The design he proposed was insane by the standards of the time. 3 steel arches, with the center span stretching 520 feet. No bridge had ever used steel as the primary structural material. Steel was for rails and tools, not for bearing the weight of entire trains hundreds of feet above a river. Iron was the standard, and even iron bridges were pushing the limits of what people trusted. Eads didn't care. He'd done the math, and the math said steel could handle compression loads that would crush iron. The problem: nobody had actually tested this at scale. The material properties of large steel components under real-world conditions were basically theoretical. Eads was proposing to bet millions of dollars and countless lives on theories. Then the construction began, and everything went wrong in exactly the ways you'd expect when you're attempting something that's never been done before. The caissons, those underwater chambers where workers dig down to bedrock to set the foundations, had to go deeper than any caisson ever built. The riverbed kept revealing new layers of sand and mud. Workers were going down 100 feet below the water surface, working in compressed air so intense it gave them the bends. 14 men died during foundation work. Not from accidents, from the air pressure literally boiling nitrogen in their blood when they surfaced too quickly. Up top, the steel itself was a nightmare. Eads had contracted with multiple steel mills, and each batch came back with slightly different properties. Some pieces were brittle, some were too soft. The quality control was so inconsistent that Eads eventually had to build his own testing facility just to verify each component. He rejected entire shipments, causing massive delays and cost overruns. The arch assembly was even worse. Eads designed a wrote about standing on the eastern arch as it cantilevered 200 feet out over the river, anchored only on one end, swaying in the wind. He describes looking down at the Mississippi, thinking about his wife and 2 kids, and wondering if Eads actually knew what he was doing or if they were all about to die for some rich man's ego project. Brennan stayed. He needed the money. Lots of workers needed the money. They were mostly Irish and German immigrants, making about $2 a day to risk their lives in compressed air chambers and on unstable steel structures suspended over a river that had killed thousands. When someone died, and someone died every few weeks, the crew would hold a quick service, then get back to work. Bills didn't stop coming just because your friend drowned or got the bends. The caisson workers had it worst. Shifts were limited to 2 hours because the air pressure would literally cook your brain if you stayed down longer. Men would come up shaking, nosebleeds streaming, joints aching from nitrogen bubbles forming in their tissues. The chief physician, a doctor named Jaminet, kept detailed records of 119 cases of decompression sickness. 14 died. The rest lived with chronic pain, weakened hearts, destroyed joints. Here's what gets me. Those workers knew the risks better than anyone, but they also developed this strange confidence in the bridge. When you've spent months assembling every rivet, when you've seen how each piece fits together, you start to trust the structure in a way that outsiders never could. By the time the bridge opened, the workers were more confident in it than most engineers. The first train crossing on June 14, 1874, was a test run. The locomotive was loaded with extra coal and iron ingots to simulate maximum weight. Every newspaper in St. Louis sent reporters. Crowds lined the riverbanks, and the bridge workers, including Brennan, stood right there on the structure as the train rolled across. If it was going to fail, they were going to die with it. That's the kind of faith you have when you've built something with your own hands. But the most dramatic near-failure nobody talks about happened in 1896, during a particularly nasty ice jam. The temperature had been fluctuating wildly, warm enough to break up the river ice, then cold enough to freeze it again in massive chunks. These ice floes started piling up against the western pier, stacking higher and higher, pressing against the foundation with millions of pounds of force. A young assistant engineer named Robert Moore was monitoring the situation. He noticed something terrifying. The pier was starting to shift. Not much, maybe a quarter inch, but it was moving. The ice was literally trying to push the entire pier downstream. Moore sent an urgent telegram to the chief engineer, who sent back a simple message: "Trust Eads's foundations." Moore didn't trust them. He evacuated the bridge, stopped all train traffic, and waited for the pier to collapse. He sat there all night, in freezing temperatures, watching that pier by lamplight, certain he was about to witness a catastrophe that would kill hundreds. Morning came. The ice broke up. The pier shifted back to its original position, perfectly plumb. Eads's obsessive foundation work had held against forces that would have destroyed any other bridge of that era. Moore wrote in his later memoirs that this moment changed how he thought about engineering. It wasn't just about calculations and safety factors. Sometimes you had to account for the obsessive personality of the original designer, the fact that Eads had been so paranoid about failure that he'd overbuilt everything by margins that seemed wasteful at the time, but proved essential later. The real mystery didn't get solved until 2003, when a team of civil engineering professors from Washington University decided to do a comprehensive structural analysis using modern finite element modeling. They got access to the original blueprints, which, amazingly, still existed in the archives, and started running computer simulations that would have taken Eads a lifetime to calculate by hand. What they found was shocking. Eads's calculations were wrong, not slightly off, substantially wrong in multiple areas. His estimates for wind loads were too low. His calculations for thermal expansion were based on simplified assumptions that didn't account for the complex interactions between multiple arches. His understanding of material fatigue was basically non-existent, because material fatigue as a concept wasn't well understood in the 1870s. By modern standards, applying modern safety factors, the bridge shouldn't have been approved for construction. It definitely shouldn't have survived 130 years of heavy use. So what happened? The Washington University team dug deeper. They used laser scanning to measure the actual dimensions of the existing bridge components, then compared them to the blueprints. And here's where it gets interesting. The bridges built didn't exactly match the plans. Workers had made field adjustments. When pieces didn't fit quite right, they'd modified them. When Eades's specifications seemed impossible to execute, they'd improvised. The construction supervisor, a man named Henry Flawed, had apparently made hundreds of small decisions that deviated from Eades's original design. He'd added extra bracing here, reinforced connections there, adjusted angles slightly to account for real-world conditions. These modifications weren't documented. They weren't in any official plans. They were just the accumulated wisdom of experienced workers who knew that theoretical designs needed practical adjustments. And those adjustments, collectively, had made the bridge stronger than Eades's calculations predicted. But there was something else. The computer models revealed that the arch geometry created stress distributions that the 1870s equations couldn't capture. Modern structural analysis uses tensor calculus and differential equations that didn't exist when Eads was working. When the team applied these modern mathematical tools to the actual bridge geometry, they found that the arches were distributing loads in ways that maximized the strength of the compression-based design. In other words, Eads had arrived at the right answer using wrong methods. He'd intuited structural principles that wouldn't be formally proven for another 50 years. His years of walking the river bottom, observing how natural rock arches and geological formations handled stress, had given him an instinctive understanding that surpassed the formal engineering knowledge of his time. The metallurgical analysis added another layer. Samples taken from the original steel showed that the specific heat treatment and forging methods used in the 1870s had created a grain structure that made the steel more resilient than modern equivalents. We'd actually lost some of that manufacturing knowledge when we industrialized steel production. The bridge was built with a type of steel we couldn't reproduce today if we tried. The final piece of the puzzle came from examining the repair and maintenance records. Over 130 years, the bridge had been continuously monitored, adjusted, and maintained with an obsessive attention to detail that most modern structures don't receive. Every rivet that showed signs of stress had been replaced. Every expansion joint had been calibrated. The bridge had evolved, adapting to new loads and new conditions, constantly being refined by generations of engineers who understood that they were maintaining an irreplaceable piece of infrastructure. The Washington University team's conclusion: the Eads Bridge survived because it was the product of obsessive attention to quality, fortunate material properties, accumulated practical wisdom, and continuous adaptation. It wasn't a triumph of calculation. It was a triumph of craftsmanship, intuition, and obsessive maintenance. The Eads Bridge is still standing, still carrying trains, still spanning the Mississippi after 150 years. Most of the bridges built in the same era are long gone, demolished, collapsed, or replaced. But this mistake bridge, this project that everybody said would fail, has outlasted almost everything else from that era. What does that tell us? Maybe that our modern obsession with perfect calculations and safety factors is missing something. Maybe there's wisdom in the old approach, hiring obsessive perfectionists, trusting experienced workers to make field adjustments, building things with materials we understand deeply even if we can't model them perfectly. Or maybe it tells us something simpler. That progress isn't always about being right. Sometimes it's about being so afraid of being wrong that you overbuild, overtest, and overthink everything until you accidentally create something that transcends your own understanding. Eads didn't build a bridge that matched his calculations. He built a bridge that was better than his calculations because he was too stubborn and too paranoid to accept anything less than perfection. The bridge is still there, crossing the Mississippi, a monument to the idea that sometimes the best way to succeed is to be so terrified of failure that you refuse to accept the limits of what's supposed to be possible.